claim I can because, as I told you guys, every regular Markov chain does have a stable vector. And this system of equations is supposed to describe the stable vector, basically. Then it stands to reason that I could always reduce my matrix that I get by turning this system of equations into a matrix. I should always be able to reduce it so that it's solvable like this. I should get ones on the diagonal here so that I know exactly what the entries of my vector are. But then to be able to do that, that means that this last row has to just be all zeros. Otherwise, I can't reduce it. And if this wasn't 0 or something, then there's no solution or whatever. So it looks like always I'm going to have this extra row of zeros at the end, which really means that I don't need all of these equations. They're redundant. So it looks like maybe I can throw out an equation. I can save myself some trouble and just get rid of one of them. And my advice would be don't get rid of this one because it has ones for all of the coefficients, and that's really nice. Everything is 1. So I would keep this guy here. And instead, maybe I'd get rid of one of these gross ones with decimals all over the place. So maybe what we're going to do here is just say sayonara to this one. And we'll just keep these top 3, and we'll solve that system. Because I don't need, if I end up including the 4th one, it won't hurt anything, but I'm just going to end up getting a row of zeros representing it anyway. So it'd be kind of a waste of my time to include this last one and try to solve it. So that's what we're going to do. Save ourselves just a little bit of work. The whole philosophy of doing mathematics is supposed to be to work smarter, not harder. And so we're just going to get rid of this last equation to save us some trouble. So here we go. Let's solve this system now. Or I just get rid of that last equation. And so again, that works in general here. It's sort of forced upon us that one of these equations is just sort of extra. Okay, so now I have this system, so let's go ahead and solve it. This is 3 equations with 3 variables. So I don't really want to do elimination method or substitution or anything. I would much rather do a matrix method here. I'd much rather reduce my matrix. So that's exactly what we're going to do. So let's translate this into an augmented matrix. Hopefully you guys haven't forgotten how to do this from chapter 5. And it's been a while. We took sort of a detour in chapter 7 where we didn't do anything with matrices almost. But now we're back. So let's go ahead and write down the augmented matrix. So the first row will just be 1, 1, 1, 1. All ones. The second row will be -1, 0.2, 0, and then 0. So there's no W3 in the second equation, so this is a 0 because I'm missing the W3. And then the last row will be 0.6, -0.6, and 0.4, and then 0. Okay. So this will be the matrix that I solve, that I try to reduce. Okay. So I'll go ahead and walk through it because maybe it's been a while since we've done one of these, and also it's just good to see this process in full. So I'll go ahead and finish this off. So let's go ahead and reduce. I need a 0 here. I already have a 1, so I'm just going to add this row to kill this -1. And so let's add 1 times the first row down here. So I'm going to get 0. 1 plus 0.2 is 1.2. 1 plus 0 is 1. 1 plus 0 is 1. And to save myself some writing, I am now also going to, this is 1.12. I am also going to go ahead and just take care of this guy in the same sort of step. So I'm also in this step going to add -0.6 times the first row. They decided they're mowing the lawn outside of my room right now, so hopefully you guys don't hear that. I don't know if my mic is picking up that lawnmower. It's quite loud. Sorry about that if you can hear that. I'm going to take -0.6 times the first row and add it to this last row to cancel out this 0.6. So what happens if I take -0.6 the top row and add it to the second row? Well, -0.6 plus 0.6 will be 0. -0.6 plus -0.6 is -1.2. -0.6 plus 0.4 is -0.2. And -0.6 plus 0 will be -0.6. So if I do those 2 steps, add this to this row and add -0.6 this row to this row, this will be my resulting matrix. This is what I'll get here. I didn't want to write out every single step nitty-gritty just because we've done a lot of matrix stuff before, so I just want to refresh your memories a little bit, but not write down every detail. But this is my resulting matrix. Okay, so now what do I need to do? I need to get maybe a 1 here, but so I have a couple options. One, I could just go ahead right away and divide this row by 1.2 to make a 1 here, and that's totally fine. On the other hand, I can't resist. I see a 1.2 and a minus 1.2. I know eventually I need a 0 here anyway, but they already are opposite signs. So before I get a 1 here, I'm going to jump the gun, and I'm going to add this row to kill this negative 1.2, because I just, seeing the opposite signs, I just can't help myself. It'll just make things easier in the long run. So let's go ahead and do that. Let's just add the second row to the third row to kill this minus 1.2. So just straight up add down. 1.2 plus minus 1.2 is 0. 1 minus 0.2 is 0.8. And 1 minus 0.6 is 0.4. So here's my new matrix now. Okay, so that's going to be nice for us. Now I can just divide this by 1.2 to make a 1 here. So I'll go ahead and do that next. Let's get a 1. So continuing up here, just divide the second row. So maybe 1 over 1.2, row 2, Let's just divide the second row by 1.2. I know I'm going to get a 1 here. You might have to think for a second, what's 1 divided by 1.2? 1.2 is 6/5 as a fraction. So 1 over 6/5 is 5 over 6. So I'm going to write it as a fraction, 5 over 6. This will also be 5 over 6. I checked that before class just to make sure I had that right. And I'm going to write it as a fraction because as a decimal, it's an infinitely repeating decimal. With 3's repeating forever. So it's just easier for me to write it as a fraction. So if I divide 1 by 1.2, I get 5 over 6. And then I have 0, 0, 0.8, and 0.4, and then 1.1. Okay. Cool. So here's my new matrix. So my last thing I need to do in this middle column is get a 0 here. So I'm just going to subtract the second row from the first row, like row 1 minus row 2. So that these 1s will cancel out. So I'll get 1, 0. 1 minus 5, 6 is 1, 6. So I get 1, 6 again. And then I am good. My second column is done. Like that. So now I just have to deal with that third column. I need to turn that 0.8 into a into a 1. So I'm going to divide that last row, by 0.8. 0.8 is 4/5. So I'm really multiplying by like 5 over 4 or something. That's 2/5. So anyway, the point I'm going to make here is that you should check this yourself if you don't believe me. If I divide the last row by 0.8, this will become a 1 because I'm dividing by itself. 0.4 divided by 0.8 is 1/2, 0.5. So work that out yourself if you don't believe me. But that is what that is. And so here's my matrix. I'm almost there. I just need to make zeros in these two spots. And I'll go ahead and sort of do that in one step again here. Just write down the results. So what do I need to do? I basically need to take negative 1/6 plus the first row, and then negative 5/6 plus the second row, right? That's what I need to do. So if I take negative 1/6 times the third row and add it to the first row, I'm going to get 1, 0, 0. And then what's 1/2 times negative 1/6? 1/2 times negative 1/6 is negative 1/12. And then I need to add to that 1/6. And I think the answer here then is 1/12. Yeah, I think we're going to get 1/12 here. And then I'm going to take negative 5/6 and add it to the second row. So I'm going to get 0, 1, 0. And then I need to ask, what's 1/2 times negative 5/6? Well, that sounds like negative 5 12s. But plus 5 6. That's negative 5 12s plus 10 12s. So I think we just get 5 12s. So 5 12s. 0, 0, 1, and then 1/2. Okay. Ta-da, we're done. We've reduced our matrix. We got this. Notice it's fully reduced. I have 1, 1, 1, and zeros everywhere else. This is great. It's reduced, and I have a unique solution. And these guys give me the solution. So let's summarize our findings. That, we got to remember why we just did what we did. What we found is W1 is 1/12, W2 is 5 12s, and W3 is 1/2. Okay, so W then, the stable vector, has to just be 1/12, 5 12s, and 1/2. And as a sanity check, technically we're done, but just to make sure that everything was correct, we might just want to make sure, like, do these three numbers add up to 1? Because that was a stipulation. And that's sort of a good way for us to check our work really quick. And so let's just do it quick, just as a check, to make sure everything went okay. 1/12 plus 5 12s plus 1/2 is 1/12 plus 5 12s. I need a common denominator. That's 6 over 12. 1 plus 5 is 6. 6 plus 6 is 12. So that's 12 over 12, which is 1. So it looks like everything is good. This answer makes sense. And so I feel confident in concluding that this really is the stable vector. And so we are done with the problem. We found the stable vector. Okay. So this last part wasn't about finding the vector. It was just checking to make sure that what we found was correct and makes sense. And it looks like it does. Okay, good. So I'll pause here again and ask if there are any questions. Okay, doesn't sound like it. How are we doing on time? Okay. Got like 20 minutes left, and that's good because I think I'm probably done talking today. I think this is all I want to say. So, yeah, I think I'm just going to leave it at this for today. Tomorrow, I'll probably do some more examples and discuss just a little bit more about these regular Markov chains. But otherwise, take the rest of the time, work on activities, work on web work, whatever. Ask questions if you have any. And just remember that there are activities for 8.3. The first one's due tomorrow night, and the next one's due on Thursday. So if you guys have any questions, stick around. Otherwise, you have a good day. See you tomorrow.